Hello, Year 7. I just wanted to put together a video helping you revise for your upcoming end of unit test. So, what we've got here, we're going to have the properties of metals and the properties of non-metals here. So, when you think of a metal, here we've got a nice bit of metal here, some wire. So, we can see it's shiny. It's quite weighty considering how little of it there is, so it's dense. So you've got a lot of mass in a small area. Think of, say, a fishing weight. They are very, very dense. Lead is a very dense metal. You have it being malleable, which means you can change its shape. You see, I can bend it into different shapes. And for it to be malleable, it's also got to be flexible, since you can move it back and forth. You can also make metal into wires. This has been made into a spring, and if we pull it out, you see we can actually turn it into a nice wire there. So we've got ductile. You can pull it into wires. Okay. They're also very, very good at conducting electricity, which is why we've got our copper inside our wire there. It's actually covered in an insulator, which is a non-metal, to stop me being electrocuted. Okay, so we've got a good conductor of heat and electricity there. So non-metals are the opposite of that. So they are dull, so they're not shiny. Think of a block of coal, for example. They're brittle. So if you hit a block of coal, which is just made out of carbon, it will shatter and go all over the place. And you're not going to conduct very much electricity through those. So say if you took a block of sulfur and you tried to run electricity through it, it would not work. Okay, so here we have oxides forming acidic compounds for non-metals there, and oxides tending to be gases at room temperature. So this is things like carbon dioxide. So you've got carbon plus oxygen there. And that's a gas there. If you dissolve it in water, it would go acidic. Here we have for oxides of metals. They form basic compounds. So if you dissolve them in water, they become alkaline. Oxides tend to be solid at room temperature. Think of if you've ever put a bike outside and after a while it's got a little bit rusty. So iron oxide, so that red stuff which forms on iron, if you leave it out in the rain, will basically be a solid, and it's FeO3. Okay, so down here we've got a new element being discovered that is dense, and its oxide is solid and basic. So we need to have a little look here. So we've got it being dense, that's a metal property, and its oxide is solid, that's a metal property. And let's see, it's basic, so that is also a metal property. So this is a metal. So here we have our second one here. So if we have our pH range here, so all of the ones along this bit here are acids. This one here, right in the middle, is neutral. And these ones here are alkaline. Okay, I should really call that acids. Oh, acidic. Acidic, yep, there we go. So that's our pH range there. And if you were, say, using a universal indicator, that would be green. These would be these would be kind of reddy sort of colour, and we'd end up with this bit being blue along here, bluey purple. Okay, so here we have describe a method to make neutral salt crystals from copper oxide and hydrochloric acid. And what we would do is we'd have 4 steps. We'd first mix copper oxide and hydrochloric acid. Second, we'd filter away the excess, which means the stuff which you have left over. Excess copper oxide. Okay. And then what we would do is we would evaporate away the water. So we leave it basically, you can do it a bit quicker if you put it in an evaporating basin and you warm it, or you can leave it on a windowsill for long enough and all the water will go away. And you end with crystals. So, okay. Let's see. Now we've got a task here. We've got a real world problem because sometimes you get environments which aren't the right pH. Often it's because there's too much acid in them, but in this case it's actually too alkaline for the fish. So too alkaline, so we do that as green. Too alkaline for the fish. So what can we do to make it more neutral? Well, we want to put in the opposite. So add acid to neutralize the alkaline. So what you do is it's going to start off, say if it was pH 12, you add some acid and it will shift all the way here until eventually hit pH 7. So you keep adding acid to your alkali until eventually you get rid of your alkali and you've ended up as neutral there. What would you use to test it? It would be an indicator, and e.g. universal indicator. Universal indicator. So it would go from purple to green when neutralized. Right, remember neutralized just means made pH 7. So when you've altered the pH till it's neutral. Okay, now what we'll have a look here, we've got different acids here. So we've got hydrochloric, we've got sulfuric, and we've got nitric. We've got the type of acid you get in lemons, limes, and oranges, citric. And we get ethanoic acid, which is what you put on your fish and chips. Okay. So when you have acids and they have the same concentration, what happens when one of them is stronger than the other? It's due to the fact that they can split up completely, whereas weak acids, only a little bit of them actually goes into solution and causes them to be acidic. So all of the particles split up, and in weak acid, only some of them. Strength and concentration are not the same, because you could have the same concentration but a different strength of acid. So if you had the same concentration of hydrochloric acid and you poured it on your hand, you could end up with a really serious injury. But if you took that same concentration and it was citric acid, you could pour it on your hand and it wouldn't be a problem. If you've ever spilt vinegar on your hand, you haven't been injured. It might sting if it got in a cut. I've got a cut here. If it got in there, it would sting. But if I did the same with the same concentration of hydrochloric, it would really seriously injure me. And this is because more of the acid, 100 times more of the acid, can actually get into solution. Let's see. Right. The strength of number of the concentration is the measure of the number of particles in a given volume. The strong acids have a higher pH than weak acids. Now we come to this one here. So if we have metal and oxygen, we get the metal, and we're going to chemically join them together. So what we're going to end up with is the metal plus oxygen. But the way we write that is ox and ide, oxide. And ide just means it's got oxygen in it. So that's what you get here. So if we had an example, say if we had magnesium plus oxygen, we would get magnesium oxide. So if you've got a metal plus an acid, you get two things out of it. You get a salt, and then you get the gas which you can detect with the squeaky pop test, hydrogen. And if you've got different reactivities, so if you've got a more reactive metal like magnesium, it can steal the things which weaker metals, less reactive metals, are bound to. So magnesium can kick out our sulfate from the copper. So we end up with copper being on its own, and magnesium has come in and stolen the sulfate from it. If we had a less reactive metal, though, it's not going to do anything. It's just going to sit there on its lonesome and just not react at all. So if you see gold, copper, silver, any of those, it's never going to do anything. But if you get a really reactive metal like magnesium or sodium, it's definitely going to steal the sulfate or anything else from the other metal. Now, we're going to rank these in order of reactivity. So we're going to look at one of the signs of a chemical reaction, and this is lots of bubbles. Bubbles being a sign of a chemical reaction. So we've got, in order of the number of bubbles, we've got, let's see, that would be 1, that would be 2, that would be 3, that would be 4. So that's the order. And also we'd probably get this one being hotter as well. So this one would probably give off some heat, and you'd be able to feel that in terms of holding it in your hand, and it would warm up, and you'd be able to tell that there's a reaction going on there. So in terms of order of chemical reactivity, we've got magnesium, we've got zinc, so this is most reactive. Most and least. And then down here we've got iron, and then we've got lead. They put lead on roofs because it sticks around and doesn't react. If it did react, your roof would melt, your roof would dissolve. So that's the reason why we make our roofs out of lead, and we use magnesium for chemical reactions, because otherwise we would end up with your roof dissolving. Okay, thank you very much. I hope you find this useful, and good luck with your tests.